afternoon. So, as a follow-up to Ferdinand Bell's introduction and also Ms. Galland's presentation, I will introduce the first of the four IPCEI MECT workstreams, namely the SENSE workstream, as Ms. Galland presented. The data is collected from the sensors, and so SENSE is essential in the fact that it takes and collects the data that the AI is processing. Also, it outputs the data to the users. You can make the equivalent to our 5 senses: hearing, tasting, seeing, touching, and smelling. But you go way beyond, because you can sense in the infrared, for instance, you can sense microwaves, you can sense chemical species, and over data on top of what our own senses are able to capture. And this is, of course, applied to many domains, like are illustrated there. Obviously, the mobility. Obviously, also here it's life sciences. We could say global life sciences, like agriculture is illustrated there, but also health. And you also apply this to personal devices, IoT. Now, all our personal devices are capturing a lot of data, all kinds of data. And so this is what SENSE is all about. It's improving these sensors, and also sometimes outputting the data. And I will go to just 2 slides of a few instances of the results already obtained by the IPCEI MECT. Next slide, please. Okay, yeah, this slide I will skip also yes, and maybe before going to the results, I will also tell you that, as Ferdinand said, like every workstream in the IPCEI MECT, this is organized along the value chain, from the materials, tools, equipment, simulation, etc., needed to design and build the chips, to the technologies that are needed to assemble the chips and manufacture them, to the component and modules that are the result of the design and are manufactured by the fabs, and to the application, subsystems, and also system applications. So all the work streams in the IPCEI MECT, for those who are not familiar with this program, are organized the same way. We have already a number of results in this work stream. Sorry, I'm not involved in it, but okay. I can tell you that we have already results in the field of millimeter wave radars, for instance. We have results in the field of the sensing of the environment, of the distance. For instance, you have distance measurement devices like LiDAR, both for automotive, for robotics, and also very micro LiDAR for few meter environment. We have results also in the infrared domain, that the thermal infrared, the sensors which are able to detect the living bodies, for instance, to do emergency braking in cars. We have also results like, I think, will be presented by Martin, in the domain of UV and which have application to the life sciences. And those are just a few examples of the results of the companies which are involved in this workstream. And I think I do not know how long I took, but I think without further ado, I will leave the floor to Martin Strasbourg to introduce in more details recent work and results of the workstream SENSE from AMS OSRAM. Okay.
Yeah, now I have to kick off this details, and with the first slide, I would just go then here. Yeah, say new trends and future products in optoelectronics. And as Julie already mentioned, we are the more than more part of the IPCEI. We are the compound semiconductors, and coming later to that, I can explain you that it's not only more than more, the efforts doing that, going to the mega trends, what it takes, are at least the same as you go to the small nodes below 5 nanometers. And yeah, I cannot spare that. Just briefly to introduce the company who's doing that. So AMS OSRAM is doing classical works in automotive and specialty lamps, not part of this talk right now. and also doing the semiconductors work. And we have the classical semiconductors made of silicon, and we have the LED and lasers and sensors, what is made not of silicon, but of various compound semiconductors. And the revenue what is created is going to automotive, to consumer, and to industrial and medical applications. And it's generated by almost 20,000 people, and among them 5,000 engineers. So it's a R&D company, more or less, even so Osram has a very long record in existing for more than 100 years. And as I said, we're doing emitters, we're doing sensors, we're doing optical micromodules and integrated circuits and algorithms. And with that and our customers, we are powering advanced technologies, and especially for visualization, illumination, and for sensing. And all these give us to the statement that light and sensor solutions from AMS Osram will enabling a safer, smarter, more sustainable world. And now enough about the adding show. Now we go to the more topical part of the talk. And looking at the megatrends in the market, this is what drives us, what gives us ideas for new products. So on the left side, the megatrends of digitization, smart living, energy efficiency and sustainability, and the market I have already introduced in the columns. And now look, some are highlighted because we are especially go for those applications and those technology solutions to introduce new products, to develop new products. And so it's for digitization, especially the projected lighting, smart surfaces, advanced displays. In a minute, I will explain you what advanced displays can be. It's also the medical imaging, it's a camera enhancement for consumer, and the spectral and light sensing. And thinking about smart living, you have, again, we are in Europe, we are automotive area, you have this dynamic forward and signal lighting, you have the in-cabin sensing, and it was mentioned by Thomas before that, LiDAR is some of the hot topics, not especially highlighted here, but still there. More important also becomes the personal health monitoring. So it's a biosensing and all what comes with that. And we have seen the meter glasses for augmented and virtual realities for sensing and visualization. That becomes more important. That is some of the trends we have to go on where the products at the end of the IPCEI should become more or less available also in the market. And it's all about vital sign monitoring, what comes often with today's consumer electronics, and what should be more reliable to give you better predictions and have also applications that are possible then to use for really having the remote medical doctor. And all this is now based on a firm bar, what is shown here in a darker color. It's energy efficiency and sustainability. And since Thomas already mentioned UVC. Yes, of course, UVC is a very important part of it. Only to take one of these things out, it's the game changer if you want to get rid of mercury in the value chain. Still, these LEDs in the UVC range are made of something like an insulator. You have band gaps of 6 eV. So when I was in university, I learned everything above 1.4 eV is an insulator. You can imagine how difficult is it to get an high level doping in such an insulating material, especially as large as a band gap, as deeper the dopant is. So it also needs to activate then the dopant. And so if you would run it at 300, 400 degrees C, everything would be fine, but you can't. So that's why we have still some research work for that, and happy to do so, to contribute then also to the removal of the mercury. And talking about more than Moore and compound semiconductors and sensing, our part is mostly done by optical sensing. And therefore, you need also several emitters. And depending on the application, you have several wavelengths that you can apply for it. And you have, on the left side here, the UVC LEDs at around 265 nanometers. Then it goes with blue, green, and out of them, white LEDs, what is mostly covered with group 3 nitrides. And if we go to longer wavelengths, to true red LEDs or lasers, and even to IREDs, then we have to change the gears and we go to phosphides and arsenides. And that is a little bit tricky because these materials are not really comparable to gallium nitride. Gallium nitride is something what is a very stiff and hard material and can even be a good device when you have a defect density of 10 to the 7, 10 to the 8. as a true semiconductor community here, you were probably very much afraid of such high defect densities. And that is also what it takes for the gallium arsenide or the gallium phosphide. Here you have to be well below 10 to the 3 of defect density to have good devices. And of course, not only incoherent light is part for sensing, some sensors require coherent light, and here we have laser material with gallium nitride, gallium arsenide, gallium phosphide materials with edge emitting and surface emitting components. So, and now, having only 10 minutes given by the organizers, I have to just focus on one, so say, technology megatrend derived from the megatrends. It's a miniaturization. Miniaturization is all around. It has started 10, 15 years ago, and now where we want to go. And the first way from LEDs, it's just go to mini LEDs. You just shrink the length as a dimension of the, and can go even down to 50 to 150 micrometers, but then the community calls mini LEDs. And you find them already in full array local dimming backlights for high quality TVs, for public information displays, so that works quite well. And they have a lot of advantages, especially they are very major, they are very efficient, and they help to improve the legacy tech due to new quality, due to being now transparent, being somehow wrapped around. And still it is a difficulty to get here pixel pitches below 1 millimeter. And then you can understand for your smartphone, for some smaller displays, this is not feasible. You have to shrink further. If you shrink further, you go to micro LEDs. And here the typical applications are images for augmented and virtual reality, consumer direct view displays like on your smartwatch or for mobile. And they are as good as OLED, but better. So we, as a company, did in the 2000 years both OLEDs and classical semiconductors. In that way, I can only say, here you see a long list of what they can do even better. Reliability, sensor integration are only a few points what are very important to it. Nevertheless, when you have very small LEDs, you have to integrate them, you have to transfer them. And the majority of such small LEDs, where then the physics comes into play, is very, very difficult. So about the laser, I just skipped for a while because I'm afraid I'm running out of time, and I will see how much minutes I'm only left only 2 minutes, no. Okay, mini LED. Here you see just the scheme, how it is. We have a mini LED put on metal traces, and they are on a transparent substrate. The protection layer is also transparent. And you can see here you can see then a microscope image of such a mini LEDs, and the applications already mentioned, automotive, interior, exterior. You can have them flexible, you can wrap them around almost every surface and have even a 3D impression for it. And now going to the micro LED applications. Fortunately, Julie said something about the Google glasses, but I just want to highlight, when you want to use it for augmented reality, you need very high density of light. You need not only kilocandela per square meter, you need megacandela per square meter. So we need to improve by a factor of 500 to 1000. And for the car interior, it looks quite nice. You can have it as well with similar requirements. Here it is very interesting to address, you have the RGB LEDs and you have a sensor in plane. This technology gives now the chance that we can have behind every display a sensor. And that means it can look like that, but often it looks like that you have only small area needed for the LEDs and a much larger area still free for using for the sensor. And that gives, for instance, then the chance to do fingerprint security on almost every display you can imagine. And on the left side, you see what is the physical principle on it. You have something like a reflection coefficient, what differs from the horned layer of the skin. And where it is not, in the valleys, you have a higher reflection, and that allows them to create pictures like this here. And you can have an integration where you have with something like below 100 micrometer pixel pitch, you can already have then a very secure integration, what gives you then this fingerprint for identification. And coming to the end of my talk, being in line with Lea, just some highlights of when you go even farther down, when you go to almost 1 micrometer pixel, you want to have also a bright emitter, and here you see something what is done with nitrides and with arsenide phosphide system. You see here the ancient, better to be seen in the middle, the ancient stone bridge of Regensburg, the two towers of the cathedral, and in between our logo. And that gives you then some impressions how small we can get here. Each pixel is less than 2 micrometer dimension, and it has something like a pixel pitch of 5 micrometer. So, and this brings me then to the end and gives just a final slide that we have several application fields, and as already mentioned, we are gratefully acknowledge the support by the Federal Ministry of now it's Economy Affairs and Energy, and by our Bavarian Ministry of Economy Affairs. It's not written here that I want to mention it, and just looking forward to your questions at the end of the presentation round for sense. Thank you.
Thank you, Martin. I invite you to stay on the stage for the question. And now we would like to host on the scene Tomas PEROTTO from ST Microelectronics, who will introduce a presentation on successful adoption of automotive image sensor for driver and occupancy monitoring solutions.
So hello everyone, so my name is Tomas PEROTTO. I'm product marketing at ST Microelectronics. And as mentioned, I will present you the successful product adoption of one of our products for automotive market. So I think a lot of people here know us, so I will not enter in the details of the company. What I've selected to do is just to present us in three bullet points. So first point, we are one of the world major semiconductor company. We compete with the biggest companies, so Sony, Samsung, Infineon, and so on. And we are 100% European. So this is an important point to us. Second point, we have 4 key markets. We have the automotive, of course. We have the industrial market with a lot of sensors. Personal electronics with all the smartphone, smartwatch, and so on. And also everything related to the communication equipment. And last point that I like to mention is that we are what is called an IDM, an integrated device manufacturer. So it means that we do everything from our own, from the R&D to the mass production. Now, regarding our product portfolio, so I work for the imaging division, and at imaging we have 5 big pillars. First of all, we have the global shutters to make cameras. We have what we call the TOF, time of flight sensor, to measure 3D, measure distance of a face, for example. We have the ambient light sensor in smartphone, for example, to measure the color accuracy of a scene. And we have the optics. But for today, for this presentation, I will just talk about the global shutter. Okay, so let's go in the interesting part. So I want to introduce this topic by talking about road safety. Because it's been years that there are reports that has been developed in European Union, showing that everything related to drowsiness or inattention lead to accidents. So I think you know that, but to avoid all accidents and to prevent all the risk that can happen in a car, the European Union decided in 2024 to have a system in all new cars sold in Europe to avoid drowsiness or inattention. So typically, if tomorrow you purchase a car, you should have a system that allows you to detect if you start to sleep or if you smoke, if you use your smartphone, and so on. Basically, how does it work? It's just a small camera that is put behind the steering wheel, and that allows to measure what happened in the car. So for example, it will detect if your eyes start to fall, if you are using your smartphone so you are not focused on the road, if you start to smoke, and so on. So one important point to mention, it's an infrared image sensor that is being used. It's mainly for night vision, because during night, we need to ensure that we can still see the driver. And in infrared, we are able to put a small LED that always illuminates the driver face. And if something wrong happens in the car, for example, if you start to sleep, there will be a sound or something like that done by the car to wake up you. Now, we see that there is a clear move from the market to not only secure the driver, but also all the passengers. In fact, now people start to know how to integrate a camera, so OEMs and tier ones, and they said, okay, is it possible to use the camera not to only detect that the driver is sleeping, but also, for example, to see if all the passengers wear their seatbelts, or to optimize the airbag deployment, for example, to ensure that there is no child that is left behind. So This point seems crazy, but last year in the US, 37 babies died because their parents forgot them in the rear seats. So it's a real use case that is requested by the car makers. And here, if we want to do that accurately, we don't need just one single camera looking at the driver. We need multiple cameras. We need one RGB camera for the algos, one IR camera for the driver, one wide field of view camera. And we see that there is a kind of trade-off between having the safety of the driver and the passengers and also the cost. So when I say cost, of course, this is a financial cost, but it's also the time scale, because we take more time to produce our car, and it's also the ecological cost, because between integrating 3 cameras and 1 camera, there is a clear difference. And this is where in ST, in imaging, we decided to not follow what was the market trend, but to develop an image sensor that takes all the elements required to make all this use case, and to have one single product doing everything in one. So this image sensor, you may have heard about it. This is the VD1940. This is what we called an hybrid image sensor. So why hybrid? First of all, this is because it's an RGB IR image sensor. It has a high sensitivity on the pixel, both on the RGB and also on the IR. It's a 5 megapixel camera image sensor, so it allows you to have a great field of view, up to 140-degree field of view. That's perfect for all the cabin inside the car. There is also what we call the multi-context management. So it's a name a bit complex. It's just to say that it's possible to have both stream in parallel, infrared and RGB. So when you have algorithm, it's possible to have plenty of images at the same time. And another point, the last point that is also very important. When we speak about camera, we think about privacy. What has been developed is also all the algorithm to ensure the cybersecurity. So for example, with cryptographic key, with video stream authentication, everything to ensure the safety of our image sensor. Since the beginning, we had a lot of positive feedbacks from the tier ones and also the car makers. And in fact, we won a lot of awards everywhere in the world. So in Europe, because we have France in the automotive industry, but also in the US, in Japan, Korea, China. At a point that this product has become now a kind of standard product in the cabin, and all the car makers request to have it. So we are pushed now by the competitors who all want to have the same kind of sensor, because it's a kind of recurrence now that we have on the market. So that's good for us, because we understood the market, we understood the constraints, and we have developed a product ahead of the market, ahead of our competitors, that is now being used all across the world. And now, the last slide, so this is the last point, just to make a wrap up. If you need to remember this presentation in 3 points, first point, ST, we are an IDM, integrated device manufacturer. We developed our own chips. Second point, we do innovative design. So we don't just follow what the market wants. We try to find something different, a different approach. And last point, we are doing world-proven solution. So this product is an example of what we are doing. And they are products that are really used and really appreciated by our customers. So that's all for me. I leave the floor to the next presentation.
Thank you, Mike. And now I would like to invite in the side Jacek KULAKOWSKI from Vigo Photonics, who will introduce, Hyperpeak new approach to optical sensing.
Thank you. When I saw that I would be presenting after AMS and STMicro, I thought it's either very high bar or beginning of a good joke. So I'm Jacek KULAKOWSKI from Vigo Photonics. I'm business developer. We have been granted a project called Hyperpeak within IPCEI mechanism, where PEAK stands for Photonic Integrated Circuits. So I'll be focusing on those devices today. So integrated photonics can be understood easily by making an analogy with traditional integrated electronics, where the carrier of information is photon instead of electron, and the main building blocks are amplifiers, polarization converters, waveguides, and so on, like in electronics. There are 3 main advantages of integrated photonic circuits: is the high speed transmission rates, up to terahertz instead of gigahertz, high also efficiency and low power consumption. In terms of integrated photonics, we can also see that this can facilitate the miniaturization and allow us to make compact devices with low power consumption, high reliability, and also reduce the packaging costs. There is already a big market for photonic integrated circuits, mainly for datacom and telecom industries. So in order to reduce the energy consumption. And since 20 years, these main big companies are operating on the market, like Intel or Infinera, providing these photonic integrated circuits for datacom and telecom industry. There are also some other companies that try to make sensors based on photonic integrated circuits. But the main problem with those sensors is that they are based on the short wavelengths, around 1 micrometer in near or SWIR range, where the absorption lines of gases or liquids are overlapping, so we cannot really do some sensing. So we cannot go beyond the telecom and datacom applications. So what Vigo Photonics has presented and declared is to do the first photonic integrated circuits in medium infrared on the commercial level, because CEA and others are doing this in research already, but we want to be the first company to offer those in medium infrared. Why I say that medium infrared is so important to go beyond telecom and datacom applications? This is the example of the for example CO gas that has stronger and stronger absorption lines, NO gas that is stronger and stronger absorption lines towards medium infrared range. As you can see, we can have absorption lines 66 times stronger in SWIR, and then even more, 23 times stronger absorption lines in mid-IR. So some gases are even not detectable in SWIR. That's why just extending the spectral range, it's a requirement to do real proper sensing. And also in medium infrared, we have low atmosphere absorption and reduced impact of turbulence, and we have very strong absorption lines of glucose, of lactate, alcohol. So we can think of all sensors for wearables, smartphones, and so on. For example, glucose has a very strong absorption line at around 8 micrometers with no water absorption. Mentioning the applications that these potential photonic integrated circuits in medium infrared could be used is mainly free space optical communication. On the right, you can see already existing solutions by Viasat or by Google. But as I said, medium infrared could open up the windows with medium infrared when there is much smaller turbulence of the air. We could think of sensors. Sorry, my slides are a bit broken. But we could also think of industrial and automotive sensors with different gases that has very strong absorption lines in medium infrared. We can think of sensors for home appliances. On the right, you can see already existing but very basic sensors for laser particle monitoring in vacuum cleaner or Schwarzkopf analyzer for hair. But really, with medium infrared, we could sense more. We could sense better in better resolution. Also in wearables for blood monitoring, lactate, alcohol, glucose, and so on, breath analysis. These are all applications that could be opened up, as well as in smartphones. So Vigo is a company of more than 38 years of experience. We have 250 employees. We are fully located in Poland, where we have our own foundry, semiconductor foundry, and what we are going to propose is as I said, photonic integrated circuit in medium infrared, consisting of ceramic carrier of laser drivers, quantum cascade lasers on a chip, waveguides, detectors, and readout circuits, all to make a sensing platform for the customers. Plus, we don't want to only focus on our foundry and making those, but we also want to offer PDK, so library, process development kit library with all the elements for designing a chip like that. This is just an examples of the building blocks that we are working on, like waveguides in medium infrared, couplers, converters, gratings, and so on and so forth. We have mainly the specialty in detectors, in QCL lasers so far, because this is our core business for Vigo. But we must, within Hyperpeak, this is an 8 years project, we must do a whole platform. So on the current developments node, we are currently working on integration of QCLs and detectors with waveguides. We're working on packaging. And as soon as we want to offer foundry for making PICs and library for designing the platform, we also want to showcase the prototypes. So we already have a free space optical communication prototype ready. Now we are working on gas analyzer prototype, on driver condition monitoring prototype, and so on and so forth, as shown, just to also showcase the technology potential. On the left, you can see our current facility near Warsaw, Poland, with our reactor, with photolithography rooms, assembly line, and another reactor for growing semiconductor structures. And now within Hyperpeak, we have a total budget of 253 million euros for 8 years. And the main budget is for making a factory equipped with design, manufacturing, and packaging facilities. So that the team for the project consists not only with Vigo, but also with some other partners throughout Europe. But we are the project manager with our 3 professors that lead the main developments. We have many engineers. We are very much an research and development company. So to sum up, what do we want to offer within this Hyperpeak project within IPCEI mechanism is, first of all, we want to unlock the potential of mid-IR, which we believe it's the very good platform for sensing. We can offer foundry. We can share the project resources. This is very important, that if the customers comes to us, we can help. We can both fund the development. So this is a cost saving for our customers. And then we can support with the PDK. We are flexible in collaboration models, and we want to build the ecosystem around these peaks. That's from my side. Thank you very much.
So, good afternoon, everyone. My name is Sandra EGER. I work for AT&S in Leoben, Austria, and together with Gerhard Döll from ZEISS in Germany, we lead the Workstream Think. Today, it's my pleasure to introduce you to the Workstream Think and give you some insights. Think addresses the microelectronics value chain of energy efficient and secure data processing and data storage at all levels. This means in particular materials, tools, equipment, front-end and back-end packaging technology, chip design and fabrication. And of course, the applications which are enabled. Think covers a wide range of applications: automotive, industrial, communications, health, security. Europe is a leader in materials and equipment and has expertise in chip design and manufacturing. In particular in RF, embedded memory, power and sensors to achieve a low power system oriented approach. And components for greener, safer processing are needed. The system approach is essential. Now that we have clarified with what Think is in general, I would like to introduce you who is Think. With around 30 partners, direct partners, we have a broad spectrum from all over Europe. Almost half of them are from Germany and France. They include big names such as Robert Bosch, Infineon, NXP, or Continental. But many other nations are also represented, like Romania, Italy, and Austria, for example, to name a few. In addition, there are 10 associated partners and who are also working on sharing their expertise and their work as part of this workstream. Within Think, the goal is to develop and deploy the latest generation of digital front-end and packaging technologies, chips, and systems to keep Europe in the leading edge of this enabling field. Therefore, we develop and apply the latest families of materials, equipment, and tools to support it. This aims to keep Europe at the forefront of innovation. The target is broken down into 4 different work packages. The work packages are in all work streams the same. The areas of interest include the following. Let's start with work package 1, material simulation tools and production equipment. Here, Think focuses on material simulation and production equipment for the semiconductor value chain. Within work package 2, the semiconductor technologies and smart manufacturing and packaging and test, THINK faces challenges involving high reliability, reducing dimensions, increasing throughput, and maintaining cost-effectiveness standards in manufacturing, packaging, characterization, and test. So THINK covers manufacturing, packaging, recycling, cost-effectiveness standards. Work Package 3, Components and Modules, deals with groundbreaking techniques needed for various memory components, especially in power device architectures. And last but not least, Work Package 4, the Subsystem and System. A work package aims to industrialize building blocks for vehicle computer control, HPC, and other systems involving AI. Integration is a key to achieving seamless functionality and performance in complex systems. So we now move into an exciting part of our workstream, two forward-looking presentations that highlight cutting-edge developments in intelligent systems and semiconductor technology. First, we welcome Tomas BORT from MicroftMind. He will present on intelligent sensing at the edge, transforming maintenance through autonomous predictive analytics. And following that, we will hear from Marcello COPPOLA of ST Microelectronics, who will delve into 18 nanometers FDSI with embedded non-volatile memory technology platform and devices. So please join me in welcoming our speakers as they share their results, their great results, and their implications for the future of the intelligent systems and semiconductor innovations. Thank you very much.
Good afternoon, ladies and gentlemen. I'm also very delighted to be here with you. As you already heard, my name is Tomas BORT, and today I'm here to share how we are transforming industrial maintenance through autonomous predictive analytics. I'm going to show you how we are putting autonomous intelligence directly inside industrial sensors, and thus eliminating delays, costs, and dependencies that are quietly undermining European competitiveness. I'm representing MicroftMind, and we are direct partners in both Sense and Think workstreams. So today I'm going to balance between these two workstreams, and also I hope that I am somehow bridges these two domains. Intelligent sensing that thinks autonomously right where the decision matter most, at the edge. Now let me paint a picture at the beginning that I think happens every day across Europe. When it's 2 a.m. and a critical production line unexpectedly stops. By the time engineers arrives, diagnose the problem and restart operation, company can lose 50,000 euros in production and miss delivery deadlines. Unfortunately, I'm quite sure that this scenario plays out hundreds times daily across European industries. The hidden cost of reactive maintenance is quietly weakening our competitive position. Right now, many companies are also trapped in cloud-dependent model. The raw sensors data gets shipped to the cloud for processing, and insights travel back. But here is what it really costs. For example, a 15 minutes delay to detect any failing become a 6-hour production shutdown. There's a huge amount in cloud infrastructure cost for a mid-sized manufacturer. Critical decisions made with yesterday's data in today's fast-moving world. This isn't just inefficient, it's a strategic vulnerability. And yes, the latency and bandwidth limitations are killing our ability to compete with real-time manufacturing intelligence. So, now imagine this instead. Sensors contain an autonomous machine learning module that learns what normal behavior looks like for that specific piece of equipment in that specific environment. When something unusual happens, it knows immediately, not in 15 minutes, not after cloud processing, in milliseconds. Each sensor can adapt to its specific operational environment, and the sensor thus distinguishes between expected and unexpected behavior for individual devices. This isn't just faster, it's fundamentally different. Instead of sending raw data to the cloud, you are sending their high-level intelligence. And that's how we call it. We call it an autonomous edge intelligence. The sensors are capable of learning what's normal for its specific location, equipment, and conditions, and then alerts only when something unexpected occurs. And this is even where it gets exciting, because our embedded machine learning modules do not just detect problems, they evolve. They get smarter with every operation. These autonomous machine learning modules are designed specifically for resource-constrained embedded environments, unlike traditional systems requiring pre-trained models and some data scientists behind. Our algorithms learn incrementally directly from operational data using less, than, 200, 300 kilobytes of memory. So you don't need no cloud, no connectivity requirements, no data privacy concerns. This means that a system that can adapt to seasonal changes, to what the day of week is, to different operating conditions, even some gradual wear patterns or everything. Based on the past, in present time, you can learn how the future can look like. Let me be clear, our core algorithm models have been validated during a few proof of concepts we already conducted. We are prepared, of course, for some more. And we have achieved by those proof of concepts some remarkable breakthroughs. For example, our incremental learning algorithms are optimized for, as I said, resource-constrained environments. Edge-based AI can actually outperform cloud approaches for real-time anomaly detection. But something that surprised even us is that autonomous adaptation proves more valuable than initial model accuracy. It means that the ability to learn and adapt on site creates more value than having a perfect model that cannot evolve. The opportunity that lies ahead us are quite great. We rapidly expand into new industrial sectors, just for example, to mention photovoltaics, standardize edge AI across critical European infrastructure, and most importantly, we want to build European autonomy in predictive intelligent technologies. Something that exactly what our IPCEI for microelectronics and communication technology envisions. We are Microsoft Mind, a Czech innovation company with, I hope, global ambitions. We do not just develop theoretical algorithms. We want to bridge machine learning algorithms with real-world constraints and also opportunities. Our algorithms are homemade, developed in our company, and they are developed with embedded limitations in mind from day one. And I want to also mention our presence or our membership in Czech National Semiconductor Cluster, because there, plus being a direct participant in both Sense and Think workstreams, we are positioning at the intersection of the semiconductor innovation and industrial application, as I hope. So that's it. That's us, and that's what we are doing, and that's what I wanted to present here to you. I'm obviously open to any discussion regarding this, regarding how our autonomous edge intelligence can accelerate our IPCEI objectives while strengthening European industrial leadership. Thank you very much.
Okay, good afternoon to everyone. I'm delighted to be here. Today, what I'm going to present is really our activity in Things. ST is, you know very well who we are. We are involved in different activities. We are working in the embedded PCM. We are developing new MCU with AI integrated. So this is what we call embedded AI capability core. Then we also we are developing new APU with the connectivity, so targeting the 4034 nanometer. We also have some activity related to sub P28, so means new MCU targeting a smaller node, and also MCU targeting multiple protocol. Here also you can see some picture of what we have already announced, but a lot of is coming in the coming years in terms of development, also in terms of innovation. Another important point is really we do also a lot of research in EPROM at the advanced RF tag. In this picture, you see what is available today, what we are able to sell on the market in terms for the STM32. So we are leading this market for the general purpose. Still in 2024, we are first worldwide. Also, we are leading the secure microcontroller. Is really important with what is in order to keep this leadership, we need still to invest. For this reason, in using a PCI framework, we are investing a lot for the MPU in GP 40 nanometer, and also everything beyond 28. But ST is particularly my group is not only providing the microcontroller, but also we are investing everything is around the microcontroller, because what we would like is to provide you everything in order to build your IoT device. So today, when you start to put a product on the market, you start with us with the STM32, but at the same time you need to connect sensor, actuator. You need to have the connectivity moving from the physical domain, also moving to transfer information to the cloud. So you see, we have a lot of information coming from the physical to the cloud, and vice versa, from the cloud to the physical domain when we apply actuation. This is really the typical picture for any IoT solution today available on the market. And then you can decide whether you apply, whether you start to develop your AI algorithm. In the previous presentation, you see the innovation, not doing the AI on the cloud, but pushing the AI on the edge. For ST, we are really pushing, we enable all our microcontrollers to support AI. This support could be done either in hardware with a specific accelerator, but also we can support AI on the sensing part. So now in this presentation, what I would like is just to give you what is really important, not only when we develop a microcontroller, but what is really important when you need to build, you start to put an IoT device on the product, on the market. One big factor is the BOM, is really the real cost of this kind of device. From STMicro, we are investing a lot using a PCIe to reduce the cost of our microcontroller. We have announced, we are working a lot in a low-cost microcontroller. Some has been announced this year, but a lot will be announced in the coming years using, what we are doing at the moment using a PCIe. But at the same time, is really important, as you can see in this picture, the most of the cost is coming from the hardware and the mechanical part. So for this reason, it's very important when you build your system, you think which kind of component will be part of my system, how I'm going to connect those components. Because of these are, you can get a big impact from the final cost. So today, in this picture, you see the typical architecture from IoT device. So in general, is a battery power. So you have the sensing, you have the MCU. The MCU is reading the value, the data from the sensor part. Then using a transceiver, you are able, an antenna, we are able to transmit using some specific protocol to the gateway. From the gateway, we go to the cloud where we can make all the analysis. So this is the way today. In order to reduce the cost, you can start to change a little bit this architecture. So what you can try is really try to put what we call the energy way to power this device, not only from the battery, but to have some system able to power the device, and particularly the sensing part. So in this architecture I'm showing now, you can see how we are able, for instance, to have an architecture where we still have the battery, but at the same time we start to introduce the RFID. So in this way, with a reader, we are able to get some data, and then using this data, we can transfer this data in a different manner. So but still the sensor is outside this usage. So what is a desiderata is really to completely remove the power from the sensor, so attach to the sensor an RFID, and then able to transmit this kind of data directly with the battery. you need to think when you have an IoT device, you don't connect only one sensor, but you have the IoT device is becoming an hub of sensing. So if you are able in some way to reduce the power consumed by the battery, but you start to use some other techniques like what I'm showing you, like the RFID, this could be a solution to reduce cost because you can reduce cabling, you can reduce the mechanical part, and then you connect to the sensor by wireless. But at the same time, you don't consume any extra power. In this direction, inside IPCEI, ST is developing a family of products. This family of products is called ST25. The ST25 is complementing our STM32. So what we produce, what we develop is really the tag. We have the reader, and as you can see here, we have participating to different organizations, standardization standard in order to be sure that what we have is really compatible with the major standard today worldwide. Today you can see the three type of device we have. We have the simple tag, the ST25T. Then we have the dynamic tag where we are able to connect. We have an I2C, so we are able to connect a microcontroller, and then we have the reader. So today this is the family of product available at ST. Using IPCEI, we are still evolving. The family is the same, but we are developing a new solution with the extra feature. One product we have developed is the ST25 TVC. This product is really something different than previous. One important point is really the type of the introduction of security. In general tag, there is no security at all. In this case, we have a secure communication between the tag and the reader, or the tag or the microcontroller. The technology we are using is what we call a Trust25. It's a sort of digital signature with the 64-bit password encoded. In this way, we are able to detect what are the real tag from the fake tag, because this is another important point we would like to offer to our customer. Imagine you have developed your sensor, another Chinese company can sell the same sensor with the same feature, but using this kind of techniques, we are able to identify if your sensor is the original, or if you have a sort of fake sensor in your product. Now I'm going to the last slide. So this is a real what would in this slide just to summarize, but at the same time to give you how is important the RFID. The RFID compared to the barcode, so we don't need the real to have something visible in order to get the information, is really cost effective. The cost of this kind of device is very low, but the number of application is huge. So we have the healthcare, the food, the agriculture, automotive, the space, wearable, the location. So as you can see, this kind of product today we sell in many markets. At the end is up to our customer to provide, to use this kind of device in an innovative way. What at the moment we have some project where ST is participating using this kind of device. One is really use the RFID in order to detect the crack in the bridges in the structural device. So using this kind of technology, you can know when there is a sort of in the building there is some problem. Another important point is also on the agriculture part. Today we're working with some company where we are able to connect, to combine the RFID plus with this innovative biosensing. Using this kind of sensing, we are able to calculate the real amount of water that the plant is absorbing at real time. And then this could be real a consumer device where using your telephone, eventually you can read the needs of water of your plant. Or you can use this device for real industrial agriculture. Today, there are this kind of sensors are used by big companies in order really in this picture is really the tomato plant where they measure the amount, where they need to put the water in the tomato. And this is something real. Another important usage of this kind of RFID is really in automotive. In automotive, for instance, the typical use case is real for there was the problem to have the children inside the house, the child inside the house, the car. In order to detect this, we can detect this using this kind of technology. It's cheap, but it's quite effective. Also, another place where the car manufacturer are putting this kind of solution is inside the tire, because they are able to detect the pressure of the tire. In this way, they are able to alert you if something is getting wrong. So with this, I conclude my talk.
So now we are going to have a presentation on the two remaining work streams, which are ACT and Communicate. And we will start by the work stream ACT, which will be introduced by Angelika IBERL from Infineon, to whom I would let the floor.
So I'm happy to present the Workstream ACT today. I'm not the Workstream leader. I do it on behalf of the Workstream leaders who cannot be here today. And so the Workstream ACT, this is really about power. It is about actuation. And it's about doing something, having an effect, like managing the energy flow, visualizing information or displaying information, moving, driving electric motor, and so on. And it's about, at the end, about the energy efficiency, reducing energy consumption, as it is written on the slide, but it is even more. So it starts already at the energy generation by renewable powers, be it wind or solar power, energy transmission, and then energy consumption. So it has really an effect everywhere where electricity is used. And in this Workstream ACT, it's a bit similar to what we already saw before. So we have more than 20 participants in Europe. We have, again, a very strong focus on Germany and France. And what we have here is also a nice, let's say, mix of smaller companies, of larger companies in the individual member states. And so we also have a nice mix, let's say, along this value chain. So we learned today already we have these 4 work packages: materials, tools, equipment, semiconductor technologies, manufacturing, packaging, and test, components and modules, and then finally the systems and subsystems. And on the next slide, you see a few highlights, what has been already achieved in the last 2 years. So starting really from the materials and the tools and equipments, there were some new results, highlights, coating of wafer handlers, or tools for gallium nitride equipment, building a new clean room. So we will hear, I guess, more about this in a minute from the next speaker. And what is also very interesting in this Workstream ACT, it is also a combination of different materials always. So it is about silicon. So the well-known silicon, we still see a lot of innovation in silicon. We have silicon carbide compound semiconductor, we have gallium nitride semiconductor. So it is really a very broad range of materials, which is innovated and where we still do research, but we do first industrial deployment, improving manufacturing technologies, and so on. This is also displayed here on this last slide, where we see highlights from gallium nitride. We see, again, silicon, the thinnest silicon power wafer, but then also when it comes to the system, it's then not only about the material or about the device itself, it's then also about the topology, how you use the devices. And here we already could show nice examples from some companies like Renault, I think it's shown on one of these pages, where you have new onboard charger topologies. And so with that, I already close my little talk. So it's the green work stream. It's powering a sustainable Europe. And I think, Leah, you're going to introduce we have one speaker in this session talking about silicon carbide. Okay, so.
Thank you very much, Angelika. So indeed, we have only one presentation for this work stream, which will be introduced by Eric Guyot from Soitec. And Eric Guyot will be talking about bringing value up to the system level through SiC substrate engineering. The floor is yours.
Okay, so good afternoon, everybody. So my name is Eric Guyot. I'm product design manager at Soitec, in charge of silicon carbide engineered substrate. So today, after a short introduction about Soitec, I will share with you the key features that our technology is bringing at the device level, and give you some technical updates, and so some perspectives in terms of new results and the impact in terms of, as we said, in terms of efficiency. And also I will give a few words about sustainability. So, Soitec. So we are located very close to here in the Grésivaudan Valley. So what is our positioning? So in fact, we have a quite unique positioning in between standard semiconductor materials and device makers. In fact, we are buying wafers and we are selling wafers. So we are making type of a booster to semiconductor materials. So this is what we are doing since now 30 years as a spin-off from CLAT. And our main product currently on the market is one covering mobile applications, especially some RF switches, where we have a huge, nearly 100 market share with through our licenses in terms of RF switches. So if you have a smartphone in your pocket, you have a Soitec inside. So, but in this ecosystem, we have built some strong relation with foundries, but also with design house to see how to better design with our new materials, devices enabling lower consumptions and more compact systems. So we are located, and our headquarters is in Grenoble, where we have 4 clean rooms dedicated to different wafer size or different materials, ranging from 8-inch, 12-inch SOI, mainly, of course, with a capacity of more than 2 million wafers per year for SOI. But we have also expanded this technology to piezoelectric materials for filters applications. And then we have some other locations. So the second main location is in Singapore to address the Asian market, where we are also producing SOI wafers, mainly 12-inch. And we have a partner in China for the Chinese market, again for SOI. And finally, it is as highlighted in this, no picture at this point, yes. We have a small entity in Belgium to cover gallium nitride activities. And silicon carbide, that I will discuss today, is located here in Bernin. And as already shown in the previous slides, we have built and start last year a dedicated fab for silicon carbide. So what are we doing for silicon carbide? So in the let's say ACT application, so we are discussing here about power conversion, power generation. So whatever is the step, the main building block is a switch. With a switch, you can do everything you want to do. Either step down the voltage, step up the voltage, go from DC to AC voltage, whatever. You do it with a switch. So the switch is basically transistors. And the industry has moved now to, especially with silicon carbide, which brings some better efficiency in terms of switching. So lower conduction loss, lower switching losses to target, let's say, the perfect switch. And so the main application for silicon carbide is the Tesla cars. So because the Tesla made a huge introduction in the market with the collaboration with ST. And now this was the first clearly large adoption of silicon carbide. But now you can find silicon carbide in other applications such as wind, solar also, and trains. So So, so the main building block is this switch, which is transistors, where the current is flowing from the bottom to the top, and the functional layer being this one, which is architecturally grown on top of the substrate. So what we did at Soitec is to think about what Soitec could do with this on this topic about the quest for the perfect switch. What can we do with our toolbox? So we first analyze what is the real function of the material, so the silicon carbide materials here. What is the function of the substrate in the final function, and how can we improve it? So in fact, we evidence that this material is, so usually the thickness is 350 microns. In fact, what is really important is the top surface, because the top surface is the seed layer for the active layer, which is here. But more or less, the rest is just a mechanical support, heat spreader, and a contact, mechanical contact, electrical contact. So we said that rather than using a bulk material with the full thickness with the high quality single crystal silicon carbide, let's move to a sandwich where we have just what is enough, just 0.5 microns of high quality silicon carbide on top of an alternative material, which is again silicon carbide by a polycrystalline material. And having a polycrystalline opens the door to, let's say, fine-tune and adapt the composition and the properties. So in that way, by bringing two different materials in a stack, in fact, we combine the best of two worlds, which brings some, let's say, value at the device level. So as I said before, one of the key points is to improve the efficiency. So efficiency means conduction losses. And here, since this material is highly doped, the electrical resistance is strongly reduced. So it means that the on resistance of the switch will be strongly reduced. In parallel, we have so recently proved, and I will show you some results, that we have also in parallel, in addition to this, improved the switching losses. And last but not least, since we are targeting some, let's say, sustainable applications, it is quite well known that silicon carbide synthesis is quite consuming in terms of energy. You need, roughly speaking, 2 to 3 weeks to prepare 50 wafers at a temperature of more than 2,500 degrees. So it means that the temperature and the energy needed to make the preparation of the substrate is quite important. And here with this technology, we can cut this energy by 4 because this material is grown at a much lower temperature, and this one is reused. So the reuse is what, in fact, it's the smart cut, the technology that we are using since 30 years for silicon. Here we have slightly adapted the technology to silicon carbide, and the basic idea is the following one. So we start with a standard silicon carbide single crystal that we buy from the market, and we reuse it. We reuse it by cutting just a thin layer. So that's the basic idea, and bonding it to a specific silicon carbide polycrystalline material that I've explained. So based on this technology, then I will cover and go very rapidly through some key results that we have recently highlighted. So we skip this one. So the main point is to see that with this technology, we can strongly improve the on resistance. So the on resistance is the conduction losses. And as you see, the industry is struggling to reduce this on resistance. And as we reduce this on resistance, the contribution of the material of the substrate is increasing. It means that the weight and the advantage coming from our technology will be further increased as the industry moves to further technology nodes. So this is what we have demonstrated on a typical automotive application with some partnership at the European level with Bosch Semiconductor in that case. And we have demonstrated a strong on resistance together with some, without going into details, some what is called third quadrant here on the body diode at room and high temperature, so meaning at the working temperature. In addition to this, we have also improved and demonstrated that the switching losses can be strongly reduced even at high temperature, which is typically the working point in a typical high power and high power density applications. And last but not least, so without again going to details, we have also evidence recently that even in terms of reliability, there is a well-known, let's say, a degradation mechanism in the silicon carbide world, which is called bipolar degradation. So something that is rooted to the crystal defects. And we have recently evidence that thanks to our technology and the use of hydrogen in the cutting methodology, we can, let's say, make those devices and those defects, let's say, immune to degradations. So without going to details, so let's say that our technology is compatible with all the current device manufacturing processes. So it means that we are compatible with the existing fabs, and we have currently now 6 qualifications ongoing with major device players. We can also simplify slightly the process, and we have demonstrated and published 1200 volt silicon carbide diodes and MOSFETs with some improved performances, both in terms of connection and switching losses, which means further current and energy density increase for the final application, whether it is energy conversion in any applications. So, and what is also important is that this technology can open the way to even, let's say, increase the reliability of the devices built on those substrate in terms of, I mentioned the bipolar degradation, but also we even recently demonstrated some power cycling, so better lifetime in terms of final applications. And last but not least, a CO2 footprint, which is divided by 4 at the substrate level. So opening the way to have a more, let's say, a sustainable final solution serving the sustainable world. So thanks, and open for any questions if you need. Thank you.
And now we are arriving to the last workstream, and the introduction for the workstream Communicate will be done by Mr. François BRUNIER from Soitec, to whom I leave the floor.
Good afternoon, everyone. So I will present the workstream Communicate. I'm François BRUNIER from Soitec, and we represent this workstream with Uwe Bieder from Rohde & Schwarz. Okay, so I think that the broadband connectivity is really essential and for the European digital transition. In particular, and it was essential when we created this second IPCEI in 2021 with the 5G occurring and the next communication challenge. So this Communicate workstream is really the strong nerve pathway networking the brain or the think workstream and sense and the sense workstream. So in this workstream we have 29 direct partners, breakdown here in different countries, and these 29 partners bring together 134 indirect partners and more than 280 collaborations in Europe. So these 29 partners in the workstream Communicate will handle not only the RF, 5G networks, the future base stations and IoT challenges, but also work on optical communication with photonics topics here. Okay, I skipped this one, and I wanted to go down to this workstream and to have a look at the different level, the different work packages. So in the work package 1, that is led by Soitec, we will have all the secure of equipments, of the secure of critical materials, substrate, polysilicon, but also tools, equipments for characterization in D-band, that is with Uwe Rohde & Schwarz. So we have these 6 partners over there, and we will have a presentation just after me of Global Wafer, Italy, MAMC, which has has built a new bright new fab in Italy on this in this work stream. In the second work package, the semiconductor technology, We want to secure advanced semiconductors, cost efficient, low power semiconductor technologies. And just after, we will have a presentation from Global Foundries, Thomas here. And then we have the more advanced work package where we work on the components designs and the system and subsystem integration. So that's it for this introduction, and I let the floor to MEMC on the next.
Let's start. Okay, good afternoon to everybody, and my name is Andrea LAURENZI from MEMC, Italy, that is a supplier silicon wafer, and it is the third player in the world. I am responsible for data science and advanced analytics team in Italy, and today we'll talk about ensuring quality in next generation semiconductor with reliable AI models. And as we develop and implement the cutting-edge semiconductor technology, we face a key challenge: managing complexity. And you know that semiconductor manufacturing involves hundreds and hundreds process steps, and each process step has its variability. And this complexity on this variability can create a problem with the quality of the product, create a problem with the quality, and also if this complexity is not controlled, can improve the cost structure of the firms. So the variability and the complexity exist, and we want to control this variability using AI models, because AI is a good opportunity to control this complexity. And so ensuring quality and defect detection in the process steps could be a competitive advantage, can create a competitive advantage for the firm. You know that we live in the AI era, and AI permeates every business sector and also our lives. And so AI, it is not longer optional, but it is a strategic asset. And in semiconductor manufacturing, AI plays a role, an important role, in three main areas that are real-time monitoring. That means catch the deviation when they occurred, process optimization using big data, and defect detection. That means using image to detect the particles, the metals that are defect on the wafer. And it is, and we know that AI it is not only a simple improvements, but it is a revolution that changing the methods to control the complexity of the system. And now we are talking of the semiconductor manufacturing, but the same concept could be applied to every other business sector. And for example, you know that last year, in 2024, the winner of the Nobel Prize of Chemistry and Physics has been assigned to authors that worked with AI. But one of the main concerns about AI is that is what is called a black box problem. In easy term, what does it mean? It means that AI models are very powerful to give the prediction, but we don't know how they achieve this good result. And this means that the question is how much we can trust in AI models. And it is really important, especially when we work in high-risk environment, in high-stake environment. And semiconductor manufacturing presents a high-risk environment because we have to take a decision to improve the quality of the product and at the same time reduce the cost. And so we have a black box model. We have, for example, 2 images of the wafer. And this model works very well to get the prediction, but we want to know what is the confidence of this prediction, how the end user can take a good decision. And so the goal is to be able to communicate the degree of the trustworthiness in a given model prediction. And we are trying to implement this kind of model during our monitoring or process control. I add also that this topic is new in research, and there are 2 important topic research. One of it is called explainability. That means to explain, try to explain how the AI model, how is or what is the reasoning of the AI model, and try to communicate the degree of trustworthiness of the model. And now I will present you an application of this kind of models. And this is an example. For example, in a particular process step, we want to implement AI model to classify the defect of the wafer. We have a lot of defect, and we are trying to implement this kind of model that works very well, but we add also for end user this kind of confidence. For example, in this case, the model predict this kind of volcan that is a defect, and also add this other information that is the interval confidence. And we can see that the model give interval confidence that have only 1 element. This means that this prediction is good. The end user could have a good confidence on this prediction. This is another example where the model predict this, and in this case, the interval confidence have 2 elements. Also in this case, the confidence of the end user could be good. In this case is different because the interval confidence is much longer. There are a lot of elements, and this means that the decision is better. So in this case, with this additional information, process engineer can use or can take different action with respect to the reliability of the model. So in conclusion, to assure the quality of the product, that is really important to take a competitive advantage. It's important to take new models, AI models that have these elements. We need to provide to process engineer how they can trust to the model, to the prediction, and then differentiate the action that they have to take to ensure the quality of the product. Okay, that's all. I'm finished.
Our today last but not least presentation by Thomas Freudenberg from Global Foundries, but I will introduce on stage.
Hello. My name is Thomas Freudenberg. I'm from Global Foundries Dresden, and I'm managing their public funded projects and collaborative R&D projects. Today I give you or share my thoughts about reliability considerations for automotive applications. And this is within our IPCEI project, Eurofoundry. Eurofoundry is funded by the Federal Ministry of Economics and Energy, also by the federal state of Saxony and the European Union. First of all, I will give you a short overview about Global Foundry, and then I will come to the IPCEI project. Global Foundries has locations all around the world, America, Europe, and also in Asia. And Global Foundries is a semiconductor manufacturing company which manufactures these devices on a contract basis. So that means we produce integrated circuits on wafers for customers. So we have our own products you can sell as a customer on the market. This is also our key strengths as we can shift capacity and also the production from one side to the others, as all these locations work very closely together. With that, I come to the Dresden entity, which is part of the IPCEI project. So first and most important are our 2,800 employees from from roughly 47 nations. And Dresden has a clean room area of 52,000 square meters and a wafer capacity of 880,000 wafers a year. At Dresden, we have the capability, the technology platforms from 55 to 22 nanometers and provide differentiated solutions for RF, millimeter wave, automotive, as well as non-volatile memory and high voltage devices. So with that, I will come to the Eurofoundry project. So our Eurofoundry project consists of mainly 3 columns, which are aligned with the overarching goals of this IPCEI. So we are doing something for the sustainability for the production as well as sustainability, sustainable microchips. We also address the resilience of the supply chain as we are empower our customers in Europe to produce more in Europe so that there is no such a shortage as during the pandemic. And we also, with all the development we do for our technologies, we drive the digital transformation. So the project scope of Eurofoundry is the development of these novel semiconductor technologies for energy efficient, sustainable, and secure microelectronics to address our markets for automotive, industrial, and consumer IoT, as well as automotive and 5G, 6G millimeter of applications. So, and when we look into the projects, a lot of our technologies are enabled for automotive qualifications, grade 2, 1, and 0. And there was also the development for new radar sensor solutions for autonomous driving, as it is required that they are looking much more in the distance with a high angular resolution. But you cannot take the technology as it is used for consumer electronics for automotive. So automotive, there's a harsh environment, and there are other needs by the industry. So, and the OEMs, automotive industry, goes into the direction of 0 defects. So they do not want to have a defect 1 per million or 1 per billion, so that the road is going to 0 defects. So to illustrate that, there are roughly 250 million cars in Europe on the streets. And every year there are roughly 30 million new registered cars on Europe's streets. And with the transformation from combustion engine driven cars to fully battery electronic vehicles, there are also the number of chips increases inside such a vehicle. So combustion engine, 600 chips per car roughly, and for the electric vehicle, 1,300. So if you do the math, then you end up that there are every year needed for cars 17 billion chips. if you have a failure rate of 1 parts per million, then you still have 17,000 chips in the cars, or 17,000 cars which have a malfunction in Europe. So you do not want to have that. And especially the automotive industry does not want to have that. So imagine if it's just an error of like infotainment system, no problem. But if it's a problem with the airbag or brakes, then you probably will not the one who will have this car. The automotive industry or the car manufacturers put much efforts into the zero defects. And we are driving this development with them with intensive reliability studies, also for radar demonstrators in this case. So we use an electromigration, time-dependent dielectric breakthrough, hot carrier injection, as well as stress migration, hot temperature operating lifetime. And we go also a step further. We're looking into what will the package look like afterwards. We do the package simulations and do thermal humidity tests with the packaging materials of choice in order to get a chip which can be used by car manufacturer or tier 1, tier 2, tier 1 to put it in the car that it can operate under severe conditions for 20 years and longer. We are also doing the development in this IPCEI for further power management systems as used in battery electric vehicles. So can we do all these developments alone? Probably not. We need a strong ecosystem. And with GF Labs, which is empowering this ecosystem, we have the university partnerships. These are not all, this is not the full list. I just picked out the ones from Europe and the one most common. So universities, so we have Lund, University of Dresden, Berlin, but we have also collaborations with famous R&D institutes like CEA Leti, here just a couple of 100 meters down the street with its groundbreaking research it's doing every day. Also IMEC and Fraunhofer, and also very important, we have these relations here in Europe as many semiconductor manufacturers with the European Commission, France, Germany, and the Federal State of Saxony. And with all these, without this support from this government side, all these development would probably not take place in Europe. And as I hear, there are also attendees from small and medium-sized enterprises, so I want to draw your attention to something else. All these institutes, all these universities cannot simply use our sales channel to get an integrated circuit on a wafer. So we have a channel partner. This channel partner also serves other companies, so it makes it very clear. It's called Europractice. And with this channel partner, we normally enable these research partners to bring their IC or integrated circuits on a wafer. It's so-called MPWs. And within this IPCEI, we had already roughly more than a dozen tape outs on MPWs for development partners. And with that, I will close my talk and draw your attention to this side of Europractice if you are interested. So many thanks.
Okay, so before we move to the buffet, I would like, on behalf of the organization, to give a warm thank you to all the speakers today and also to all the poster presenters. And I also would like to thank the Transform Group and the facilitation group for their help for the organization, for the many meetings they have been involved in to prepare this event. And my last thank you will be for the IPCEI team, because they have done a strong work to organize today. So thanks to them. And I think we will also thank the Régie for their setting and the World Trade Center to have hosted us. Many thanks also for your question and to the audience. Thank you.